Hi everyone, welcome to this video which is all about planes. So I'm going to do a few videos, and this is not the flying type, this is the flat infinite surface type, a plane in 3 dimensions. So there's 3 ways of writing the equation of a plane. So I'm going to go through all of those 3 and maybe do one example here. So first of all, we've got here the ways that we can describe or a plane can be given. So if we have 3 points that are non-collinear, that will describe a plane. If we have a point in the plane and 2 non-parallel lines, that would define a unique plane. If we have a vector perpendicular to the plane a given distance from the origin, or a vector perpendicular to the plane and a point that lies in the plane, all of those 4 different things there, we can use those to find the equation of a plane. Okay, the first way of writing the equation of a plane, I'm going to go through this in more detail, is called the dot or scalar product form. So let's look at that in more detail. Okay, so suppose we've got a vector going through the point A. There is only one plane that goes through that point that is perpendicular to that vector. That's why planes are defined by what we call the normal vector n, the vector that's perpendicular to the plane. That is the vector that defines the plane, rather than a vector that's parallel to the plane, because there's infinitely many vectors that are parallel to that plane, but there's only one vector that's perpendicular to it, or lots of different multiples of that vector, but there's one vector, essentially one direct vector that's perpendicular to the plane. Okay, so suppose we've got a point on the plane R, and what we're saying is the dot product between the normal vector and the vector from A to R is equal to 0. So we get this expression here, n dot R minus A. Remember, R and A here are the position vectors of the point R and A. So if we just expand that out, n dot R minus n dot A is equal to 0. Remember, the dot product is commutative. So then we get this equation here, n dot R equals n dot A. Now we just have to remember what this n and what this R and what this A is. N is the normal to the plane. R is any point on the plane, any general point. So if we write that out in component form, it would be x, y, z. And A is a specific point on the plane. Another way that we can give the equation of a plane is if we just have 2 vectors in the plane, and then look at the vector that's perpendicular to those 2 vectors, and that's another method that I'm going to go through in this video. Okay, so what's the equation of the plane that goes through that point perpendicular to that vector there? Alright, so let's use the vector method. N here is 1, 3, 2. R is just x, y, z, any point on the plane, and A is 2, 3, minus 1. Okay, so on the left hand side we get that. On the right hand side we get the dot product, which is just 9. So this is one way of writing the vector equation of the plane. You'll see it written a number of different ways. A lot of the times you may just have 1, 3, 2 dot R equals 9. The other way of writing the equation of a plane, the second way, is the Cartesian form. Here's the Cartesian form of the plane, where we've just got x, y, and z, not in vector form. So you can see if you do the dot product on the left hand side there, you get 1x, 3y, and 2z. So this is the Cartesian form of the plane. Okay, show that the vector n is perpendicular to the plane containing the points A, B, and C. Alright, so we've got 3 points in the plane, so what we can do is work out the vector from A to B, which is just B minus A. We can work out the vector from A to C, which is just C minus A. Or we could have done the vector from B to C, or C to B, or B to A, or C to A. It doesn't matter which order you do them in and which way you do it. Now we just want to show that the dot product of the normal with this vector A to B is 0, which it is, and the dot product of the vector from A to C is also 0. So if you'd have done B to C as well, also you would have got 0 there. Okay, so we've got this vector equation of the plane, and we've also got the Cartesian equation of the plane. There is a third way to write the equation of a plane, which I'm going to show you now. It's okay, there's the Cartesian form. And the third way is using a point on the plane and any two vectors that are parallel to the plane. So it's this equation here in blue. So you've got a point on the plane A. You've got two vectors that lie parallel to the plane or lie in the plane. Same thing. Well, it's not the same thing, but a vector that's parallel to the plane and in the plane is going to have the same direction. And then you've got these two scalars here, lambda and mu. Okay, so what might this look like in practice? You'd have something like this. R equals 1, 2, 3. There's a point on the plane, plus mu 0 minus 1, 3. There's a vector in the plane, sorry, plus lambda 0 minus 1, 3, plus mu minus 2, 3, 4. That is the equation of a plane. These are two vectors in the plane, and this is a point on the plane. Okay, let's do a question. Let's look at this second question here. Find a vector equation of a plane through that point containing that line. Okay, diagrams always help. Got a plane here. Here's a vector that's lying in the plane, or sorry, a line. We've actually got the equation of the line in the plane, and that we know the plane is going through this point, which is 3 minus 1, 0. Okay, 3 minus 1, 0. Okay. Now, how are we going to get the vector that's perpendicular to the plane? That's what we need to do this question. The method that we're going to use to do this is called the vector product. So I'm going to zoom back and show you how to do the vector product, which is a way to do this question. If you've done a bit of physics, you'll know this right-hand rule thing that helps us. So I've got two vectors A and B. The vector product is a way of multiplying vectors so that we get a vector that is perpendicular to the two vectors that we're given. So if we've got A and B, the vector product gives us A times B, and that's this vector here, which is perpendicular to the other two. Now you can see in the context of planes that's really useful, because the way planes are defined is this vector right here. That's what we need. So if I've given you two vectors that lie in the plane, this is an extremely handy method. It's not specifically part of the course, but you can use it. Now it's this really disgusting formula, which I'm going to show you in this demo, and which you'll learn really quickly, trust me. So if I've got two vectors, I've got P and Q down here. This is how you work out the vector product. Now the vector product is another vector. Obviously it's not a scalar like the dot product, it's another vector. Okay, so to get the top number in your vector product, so I'm going for this number here at the top right now, I'm going to cover up the top row. And then I'm going to do something very much like the determinant we did when we did 2 by 2 matrices. I'm going to say this times this minus this times this. So B1 C1 minus C1 B2. That's your top number right there. Okay, second number. For the second number, again, I'm going to cross out the middle row to do the second number. And just to be extra specially tricky, we're going to reverse this time. We're going to go this times this minus this times this. So A2 C1 minus A1 C2. That is the second number right there. Okay, third number. Let's change colors here to green. To get the third number in my vector product, I'm going to cross out the bottom row, and I'm going to go back to the original way we did it. This times this minus this times this. So A1 B2 minus A2 B1. Alright, that's it, and that gives us this number right here, and we have the vector that is perpendicular to these other two vectors. Let's do one. Calculate the following vector product for these two here. Alright, so to get the top number, I'm going to ignore the top line. This times this minus this times this. So 0 minus 0, 0. Easy. Second one, I'm going to cross out this. I'm going to reverse it this time. 1 minus negative 6 is 6. Notice that time the middle number there was reversed in the order I did them. And the last number, cross out that line there and go back to the original way. 3 times 0 minus 0 times 0, which is 0. This vector here is perpendicular to these two vectors here. Isn't that nice? One more time. I'm going to do it faster this time. I'm going to do it in my head. Let's see if you can do this one. Have a go. Do the vector cross product of those two and see what you get. Okay, here it is. Let's see if you're right. To get the top number, negative 6 minus 6, negative 12. Okay, so if you're a little bit unsure, here's the calculation. Okay, negative 6 minus 6, which is negative 12. Okay, middle number. After you do this a few times, you'll be able to do it in your head. Middle number, 6 minus negative 8. 6 plus 8, 14. Bottom number, negative 8 minus negative 6. Negative 8 plus 6, negative 2. Okay, that's it. That's the vector cross product. Here's a vector now that is perpendicular to these other two vectors. You notice that you could take out a common factor of 2. So that's 2, negative 6, 7, 1. So you also could say negative 1. You could also say that this vector here is perpendicular to these other vectors. In fact, you could also say that this vector here is the vector cross product. Okay? It's just the negative of that vector there. And if we think about that, that kind of makes sense to me. Because if I'm defining that this vector is normal to the plane, then also the vector that's just going the opposite way will also be normal to the plane. Okay, that is the vector cross product. Hopefully you got that one right. If not, try some more. Okay, let's just finish off this one question. Find the vector equation of the plane through that point and containing that line. Alright, so notice that in this question here we're given the line, so I know from this equation here, I know that this point here lies on the line and the line's going in that direction. So I know the point 4, 1, 1 actually lies on the plane, doesn't it? Because it's on that line that's in the plane. So this is the point 4, 1, 1. Yep, 4, 1, 1. Alright, so to get the vector that's normal to the plane, I just need two vectors in the plane. So let's see if we can get them. What about this vector here? This vector that takes me from that point to that point. Okay, so that vector from this point here to this point here, so we call that A to B, is just B minus A. Now, it doesn't matter what order I do this in. In other words, doesn't matter if I do 3 minus 1, 0 minus 4, 1, 1 or the other way around. Of course, it doesn't matter. 3 minus 4 is negative 1, negative 1, negative 1 is negative 2, negative 1. There we go. Okay. So if I'd have done that and got the vector 1, 2, 1, doing it the other way around, that would just be this vector here, which of course would still be a vector lying in the plane, right? So it really wouldn't matter. In fact, that's a lot easier to use, isn't it? 1, 2, 1. So we've got the vector 1, 2, 1 that lies in the plane. What's another vector that lies in the plane? Alright. Well, we've got this line that lies in the plane. Wouldn't the vector in the direction of the line lie in the plane? You bet. That's this vector right here, negative 2, 1, 2. Negative 2, 1, 2. Okay. So we've got two vectors that lie in the plane. To get a vector perpendicular to those two, we're going to use the vector cross product. Let me have a go. Actually, you try it first. Can you try doing that cross product and write in the answer that you get? Okay, here it is. I'll do this once again. I'll try and speed this up a little bit. Top number, 4 minus 1, 3. Middle number, negative 2, take off 2, negative 4. Bottom number, 1, take off negative 4, is 5. There's the vector cross product. Awesome. 3 minus 4, 5. So, what's the vector equation of the plane through that point and containing that line? Alright. So, remember the vector equation, r dot n equals n dot a. So in this case here, 3 minus 4, 5. So we've got r dot 3 minus 4, 5 equals 3 minus 4, 5. And what's a point in the plane? Well, we've got lots of choices now, haven't we? There's 4, 1, 1. We could use that point there, or we could use this point here. I shouldn't say lots. We've got 2 points that are lying in the plane. I'll use 4, 1, 1. Okay, so I've got r dot 3 minus 4, 5 equals, let's do some quick calculation here, 12 plus negative 4 is 8 plus 5 is 13. There's my answer. Now if I wanted to write that out in Cartesian form, if the question was Cartesian form, it would look like this. 3x minus 4y plus 5z equals 13. Problem solved. Okay, last thing, let's have a look at these planes. Here we've got a plane in 3 dimensions. If we spin it around, you can see obviously it goes off the edge of the page here, but let's draw this one here. This plane here, if I have a look at it, is the equation of this plane here is 2x minus 4y minus z equals 6. So the normal to this plane would be 2 minus 4 minus 1. Okay, so if I was to draw a line that had 2 minus 4 minus 1 as its direction vector, there is that line, and you can see that that line there is going to be perpendicular to the plane. Let's have a look. Yep, looks good. Okay, so any vector in fact that has that direction vector will be perpendicular to this plane. Okay, hope that helps. This is your first introduction video to planes.